Now for some Hello everybody and welcome to our continuing discussion on graphing. And this Friday, I hope it is more sunny where you're at than where I am. Let us begin. Some simple functions, steps 2 and 3, asymptotic behavior, long-term behavior, increasing, decreasing behavior, will be sufficient to have a pretty good guess of what the graph looks like. But if I want to perfectly know what the graph looks like, every little bit of it, there's something missing. If I just stop at increasing, decreasing behavior, notice that I can have many functions or many graphs that are, for example, increasing. A function can be increasing in many ways. Let's visualize that. It can be increasing like this. That's definitely uphill. But it can also be increasing like this. They're both increasing. Any tangent line has a positive slope. And just saying, oh, it's increasing there, that doesn't quite tell me the shape of that graph. Something is missing. I have a similar issue with decreasing. A function can be decreasing in many ways. My writing is not very good today. I apologize. Is it ever good? No. If I look at decreasing, I have a similar issue. I can go downhill and sort of slow down, right? The tangent lines are getting flatter. Or I can go downhill slowly and then speed up. They're both downhill. They're both decreasing, but they are not the same. It's not the same shape. And to be accurate in my graph and my analysis, I kind of want to know, well, which one is happening here? All right. So let's notice the difference and similarities here between these four graphs. Think of a thin rod and you're bending it. In order for me to get a shape like this, my hands are at the ends of this rod. I have to bend it up. My hands have to move up and make sort of a half smile. Same for this one at the bottom left. My hands have to move the same way to create this bend. It's just tilted a different way. So we're going to call this we're going to say here the graph is concave up. And this one as well. The bend is the same. So I'm focusing on how the graph bends, not how it sits increasing, decreasing, because I've done that already. I'm looking for another kind of property, the bend in the graph. And if I look at the right two, my hands have to move down to create this bend. It might not be a full bend, but it has to bend down. I'll call this concave down. This one as well, concave down. Now in some cases, I might get a full bend, right? I have a longer rod, I bend it completely, hopefully it's not too hard to bend, and I get a full turn, nice smiley face. So I do think of this situation because it's easier to remember. When I'm up, I am happy. When I'm happy, I smile. Concave up. When I'm sad, I am down. When I'm down, I frown. Concave, down. So it's pretty easy to remember which is which. But know that it doesn't have to be a full turn. It could be a little half smile or a little half frown. Concave up, concave down. Okay. Now, how am I going to figure out which aspect of the function leads to the way it bends? So let's make a new page. First of all, I just want to call this step 4. The bend in the graph, we call that the concavity. Concavity. How it bends. Now, let's take a side note. Let me just take a side note. Take a function. I don't care what function. Let's call it g. Take a function g of x. Remember that this function is increasing, forgetting the 0 part of it, whenever the derivative is regardless of the function. If it's increasing, its derivative is positive. If its derivative is positive, it's increasing. Okay, so let's keep that in mind. Now let's just look at the classic concave up. Big smile. Actually, I'm going to write it at the bottom. Big smile, best case scenario. And let's call this guy f of x. So, if f of x is looking like this, concave up, what can I say about the slope values? Well, let's take some points of interest here. Let's take this point, and this point, and this point, and this point, and this point. Of course, there are many. I'm just taking some of them. And let's look at some tangent lines here. This tangent line over here, maybe its slope, it's pretty negative, right? It's pretty steep. Let's say it's -10. This slope over here, ooh, that was supposed to be a straight line. It's a little flatter, but it's still negative. Maybe it's a -2. This guy at the bottom, that's going to be horizontal, slope 0. This guy over here, well, he's a little flat, but he's positive. Let's say it's slope 2. Just examples, right? The one on the right here, it's a little steeper, but positive. Let's say its slope is 10. Just examples. So, in this situation, I have slope values among many others. They go -10, -2, 0, 2, 10, and of course they keep going, and there's stuff in between and whatever. This sequence of numbers is an increasing sequence. Increasing, right? They're getting bigger. Increasing slope values. So if I look at the function that gives me these slope values, the function is going to give me a -10 and a -2 as I move from left to right. It's going to be an increasing function. Let me say slope function. Let me say slope function. The function that gives me these slope values will be increasing. And what function gives me slope values? It is, of course, the derivative. So the derivative of the function of f is an increasing function. Is my mic still working? I sometimes wonder. So now, what does that mean? Remember up here our side note that if I have a function, I don't care where it comes from. If it's increasing, its derivative is 0. Greater than 0, sorry. Let's write the derivative like this. Now I have a function. Stop that stupid lines. I have a function right here. That's a function. I don't care where it comes from. Its derivative has to be positive. So what I have here is the derivative of the derivative of f of my function. We're going to call that the second derivative, the derivative of the derivative. So I have multiple layers of derivatives because when I take the derivative, I get a function. Who says I can't take the derivative of that function? And in fact, that second derivative is going to tell me how the graph bends. Now for short, we're just going to write this as f double prime. And that is going to be what we have to look at. Now I can do a very similar thing for concave down. If I'm concave down, my slope values will be decreasing, and my second derivative has to be negative. All right, let's get some examples going. Again, we're going to continue with more examples tomorrow, and that'll be the end of our discussion focusing on one step at a time. So, example time. Now again, it's more than anything else really. If I just do step 4 and find where the graph bends, I have no idea what the graph looks like. I have no idea. I need it as the final piece to my puzzle, but the only piece, I can't see the puzzle. So let's look at a function. X to the 4 minus 8x cubed plus 18x squared. There's a function. I don't know what it looks like. Who knows? Now, in order for me to do step 4, I need to find the second derivative. In order for me to find the second derivative, I need to first get the derivative, also called the first derivative. So step 4 is usually done after step 3 because in step 3 I would need to find the derivative and then step 4 builds on that derivative. So I can't really skip that. I have to find the derivative first. 4x cubed minus 24x squared plus 36x. That's just the first derivative. Now this is going to be a pretty okay version for me to find the second derivative, which is now the derivative of this function, right? Derivative of this function. So it is just the basic properties, 12x squared minus 48x plus 36. Now I'm going to do the table on this second derivative function. So there's going to be a lot of similarities between step 3 and step 4, except the function that I'm using my table for is different. It's going to be this guy, which means I need to clean him up. I can only do the table for multiplication or division, not addition and subtraction. Well, at the very least, let's take out a 12 and give myself a fighting chance for this factoring. That means I have x squared left, and I have a minus 4x and a plus 3. Okay, that looks way better. So hopefully we can factor that. I'll have an x and an x. I'll have a -3 and a -1. Whew, that wasn't so bad. I'm going to do almost everything exactly the same. It's just going to apply to the second derivative. I'm going to again check where is this second derivative equal to 0 and where is the second derivative undefined. Now I know for this, it's a polynomial, it's never going to be undefined, but there are going to be some functions where I need to check both, right? Where is the second derivative 0? Clearly when x is 1 and 3. Okay. So we're making progress. Now everything that I get out of this check, those are the x values that I'm going to list, and that's going to split my x-axis up into, in this case, 3 intervals. Now I list all the pieces that I see in my second derivative. By way of multiplication, they combine to give me the second derivative. 12 is always positive, but I don't want to leave it out. It's a part of it. Let's include it. X minus 3 is 0 when x is 3. In multiplication, it makes the second derivative 0. It's going to go negative to positive. Because it's a familiar x plus or minus a number, I get used to those very quickly. Anything else? I need to make sure. I need to always be sure. But repetition definitely makes these guys easier. X minus 1 is 0 when x is 1. It's just being multiplied, so it's making the second derivative 0. It's going to also go negative to positive. But do make sure for yourself that you're happy with that. I have a positive and 2 negatives. Answer will be positive. I have 1 negative here, answer will be negative. No negatives, answer will be positive. So now, this is the second derivative. No slope lines. That's not what we're doing here. So what I like to do is just have the little smiley face, or the little sad face, little smiley face, to help me remember. What does the plus mean here? Oh, it's bending up. It does not mean it's a full bend. Up or down. Sometimes not. I don't know. It's just going to bend that way. It could be just that little section of a bend. It's still the same kind of bend, concave up. Okay, so this is just a reminder for me what is happening. Let's write our sentences. Now, of course, we are still trying to make statements about the original function. F is concave up on negative infinity to 1, as well as 3 to infinity. Same rules for including the endpoints, because I have a polynomial. It's defined for all x values, which means I have y values here. I'm not going to bother calculating them. Plug it into your calculator, you get an answer. Do I have an answer? I actually do. Wow, look at me. I just didn't want to waste time to calculate it now. When x is equal to 1, I get an 11. Correct me if I'm wrong here. And a 27 when x is equal to 3. So I get y values. I can include them. There are points, regardless of what the second derivative does. So again, just want to clarify because I don't know what you're thinking. I'm totally guessing. Zeros here do not mean horizontal tangents or anything. It's the second derivative. Second derivative. Even though my table method is sort of recycled. It's a different function, different conclusions that I'm making. F is concave down on 1, 2, 3. 1, comma 3. All right. So now when I look at the critical points, in step 3, I looked at the derivative. I was searching for where it's increasing and decreasing the function. I got these interesting points out of the check for the first derivative. And if they were actual points, I call them critical points. I'm going to do the same thing here because I'm pretty much doing the same thing. I have these similar two checks. Points come out of it, but I can't call them critical points, right? It's a different situation. I need to call them something else because they're also important, but I can't use the same word. Now, before I do that, I think maybe seeing this graph might help me. Even though just from this, you are not expected to know, and I won't know. I need all the pieces. I don't know what this graph looks like. I am cheating and giving you the answer. It's not obvious from the information that we have. So please be aware of that. So I actually have a horizontal tangent here at 0. And I'm going to come through that. Of course, all that information comes from step 3. At 1, I have what I said, 11. And the bend, see the bend in the graph is up. It actually goes through a full turn. Then over here, remember at the top there, you see it bends up. At 1, it changes to bending down. Whoops, that's wobbly, I'm sorry. I don't remember if it's if it's horizontal here. I actually don't remember. Because I didn't do that step, I don't know. I can't remember. It bends down just a little bit, not a full turn, to where x is 3. And then it bends up again. Whee! Off to infinity. So I have up bend, down bend, up bend. So I have these important points that came from the check and the fact that there are points. We're going to call them inflection points. So it's very similar to, was it this page? Yes, to critical points. Except it's going to come out when the second derivative is 0 or the second derivative is undefined. So that's still my check, but now applied to the second derivative. And I have to have a point. So my function is defined there. There is a y value. There is a point. See, it's just like this one. But, of course, it can't be perfectly the same. There's another and. And the concavity or the bend in the graph must change as I cross that x value. I read that off my table. See how it changes from a plus to a minus, inflection point. Minus to a plus, inflection point. So in this case, both of these guys are inflection points because they satisfy the 3 conditions. X equal to 1, x equal to 3. They come out of my check or my second derivative. There are points. The bend changes as well. Now, I challenge you, if you have nothing else to do, can you come up with a polynomial function where I get points out of the check? They're points, they're defined, they're y values, yet the bend doesn't change, and they're not technically inflection points. It's either a plus to a plus or a minus to a minus. So let's have a very simple example. I think it's fairly simple. x minus 1. Anything that I can just do transformations on to understand is pretty simple. So I don't need this technical root, but I just want to show that I can do it and what it looks like. So of course, on the way to the second derivative, I need to find the first derivative, little chain rule, 4x minus 1 cubed times 1, which I guess I can write it, but I don't need to look at it to move forward to the second derivative. I then have 12x minus 1 squared, of course, times 1 again, which I don't need to look at. So there's my second derivative, not complicated at all. I'll do it over here. Second derivative is clearly 0 when x equals 1, and the second derivative is undefined. Never, it's a polynomial. So I get my potential inflection points, and there's one of them. I don't know if it's an inflection point yet, right? Because I've only checked the first part. But it's definitely a potential inflection point. I list everything, maybe a 12, maybe an x minus 1. Why are there brackets? I don't know, and there's another one. And together, they give me the second derivative. 12 is always positive. X minus 1 is 0 when x is 1. Goes from negative to positive. Makes the second derivative 0. Same for this one. They are copies. Now I have two negatives and no negatives. I'm bending up and I'm bending up. Now, this diagram is just for me to remind myself the bend. It doesn't mean it's a full turn. And in fact, it isn't. So I'll just write over here. My function is concave up everywhere, because I don't have to exclude 1 because it's defined there. I have a y value. The y value happens to be 0. So I have a point. I have it as a potential inflection point, but the bend doesn't change. Now, by way of one single transformation, I can very quickly graph this, of course. It is based on my basic function. X to the 4 is just like a U shape. Whoops, no, I didn't even shift it. Wow. Shift it to the right. U shape there at 1. Like that. It helps if I make sound effects. Makes it smoother. So you see, it does actually make a full turn through 1. So the left side is concave up and the right side is concave up, and they attach and make a full turn. So I need that for it to be an inflection point. I need the bend to actually change. So there is no inflection point. It has no inflection point. Okay. So for the increasing decreasing behavior, a critical point is one that comes out of my check for the first derivative, of course. And if there's a point, it's good. It's a critical point. I don't care if it's increasing and decreasing or changing or anything. I don't care. If there's a point and it comes out of the check of the derivative, it's good. But the inflection point requires a little more. Comes out of the second derivative check, there is a point, but the bend has to change. Otherwise, it's not technically called an inflection point. It's still important to me. It's still in my table. I still take note of it. I treat it just like any other point. I don't discriminate. But somewhere someone decided, nope, we're not calling that guy an inflection point. Even though in terms of how I use these points, I really don't discriminate at all. They're always important. All right, so in a way, the inflection points are easier. We don't have that many little things in examples that we did for step 3, I feel. but correct me if I'm wrong, of course. Let's do another example. We don't need these examples to be super complicated. We are not done even after this. We have to practice putting all the information together. That still is coming next week. So the discussion isn't done. We'll have more examples. Now, here I need to, of course, go through the first derivative in order to get to my second derivative. First derivative, we have done before. This is the same example I've used previously, so I'll just copy it. Hopefully that looks familiar. And if not, just trust me, that is the derivative. You have to do the quotient rule, you have to clean up the quotient rule, and this is what we get. Now I have to do the derivative on this. Now many people go, quotient rule, absolutely, I see it, it's a rational function. There's nothing wrong with that. Let's do it over here. And of course, then I have the bottom one squared. So then I have to the power of 4. Derivative of the top times the bottom minus the top times the derivative of the bottom. And then I have to simplify that because I have a reason to simplify. This times 0 means that the term is irrelevant. I have a negative 4 and one of the brackets cancel to leave 3 of them at the bottom. Nothing wrong with that. But know your options. Know your options. I have fancier properties that might be applicable. I could see this as 2 times x plus 1 to the negative 2. That means I can avoid the quotient rule, but I have to use the chain rule. So this is an OR. So I could use that approach instead and say, okay, chain rule, negative 4 x plus 1 to the negative 3. I don't love negative exponents moving forward, so I move it to the appropriate side, and you see I get the same thing. Some people love the quotient rule. I don't want to stand between you and your love of the quotient rule. That's okay. But know that you have options. And the chain rule is another option. Whichever one really gets me to simplify safely, honestly. That's my priority here. I don't want to make a mistake in simplification because I'm going to use that simplified version moving forward. So regardless of how you get it, I get the same thing, right? So the second derivative is 0 when. Second derivative is undefined when. First one, 0. Let's see if we've learned something. The second derivative, whichever one, they're the same, right? It is 0 when. For which x values will that second derivative function equal 0? This is your moment. Seize it. Never. See how we've learned? It's good. It's good. Never. Because there are no x's in the numerator, and only the numerator can make a fraction 0. It's undefined, clearly when x is negative 1. So, because these examples are fairly small, I get, again, just one contender. It's negative 1. Now, of course, in isolation, this doesn't really give me a clear impression of the graph. But if we look back and remember we have done steps 1 and 2 for this function, it's not that bad. It's a little unsatisfying if I do all this work and I still don't know what the graph looks like. I'd like to know. But this step alone is not sufficient. So negative 4 is always negative. X plus 1 is 0 when x is negative 1. It's in the denominator, so it makes the second derivatives undefined. It's going to go negative to positive, and all these guys are the same. I could merge them together. If you're comfortable doing that, go right ahead. But the simpler I make each of these pieces, the easier it is. I have 4 negatives, and I have 1 negative. So I bend up, I bend down. Let's write the sentences. I did not write my sentences here, did I? Oh well, it's over. F is, I did actually, no I did, I remember. Concave up on negative infinity to negative 1. Infinity always gets a round bracket. Does negative 1 get a round bracket or a square bracket? I want to include it, I really do. I want to include as much as I can. But I am referring to the original function. And the original function up here is not happy with negative 1. It's undefined at x equal to negative 1. So I can't include an x value that doesn't have a point. I'd love to, but I can't. So for that reason, it is not a square bracket. I wanted to, but it is not. That is not even a pretty round bracket. Come on. Man. So I have to know why I'm doing things, and then, well, I need to know what I'm doing and why I'm doing it. Concave down, I need to know the reason. Concave down, negative 1 to infinity, obviously. Again, for the same reason, I can't include that negative 1 as much as I'd love to. Can't be done. It is not allowed because the sentence, the statement, refers to points of the graph, really, in terms of the x values. Okay. Now, let's remember what came from steps 2 and 3. I really had a lot of information. We knew it was going this way, and this way, and this way, and this way, and all the increasing, decreasing information told me that. The information I got now totally fits with this, because I'm going to have to bend up to the left of course, I have to update these arrows. I didn't know how they fit. I have to bend up on the left side of negative 1, and I have to bend down on the right side of negative 1. So everything agrees with the information I would have gotten up to that point. So if you make a little mistake, maybe in your simplification of your function, something gets mixed up, you get information and it just doesn't match up. That tells you then something went wrong. All the pieces of the puzzle, everything has to agree and eventually lead me to the graph. There can't be contradicting pieces of information. So I do have a little bit of a check that if there are pieces of information, if I look at all the steps that contradict each other, that means I probably made a mistake somewhere. Finding it, well, that's another question. That's an issue on its own. But at least there's an indication that something went wrong. Oh, we're not done there, right? We're not done. We have this x equal to negative 1. Is it an inflection point or not? Let's write it out like this. Inflection point, ooh, that's ugly, at x equal to negative 1, question marks. I need to know. It's definitely a contender. It's the only contender that came out of my list. Is it an inflection point, yay or nay? It's a contender. The concavity is changing, but there is no y value. There's no y value. There's no point to call it any point, regardless of inflection point. There is no point. So you have to know all the requirements to be called those things. Sometimes they ask you, what's the inflection point? What's the critical point? Sometimes they don't. Regardless, you have to write these sentences at the bottom. They're very important. Make sure you get your intervals and your brackets right. That's where people lose marks very quickly. Alrighty, we're moving along. Maybe too fast. Let's go to one we've seen before in terms of the other steps. So it's nice to sort of fill in more and more steps of the same function. That way we can put it together and have an idea of the graph. Now, that's my function. Exponential component. I don't really know what this graph is going to look like. I know I'm going to lose symmetry. I know that. Very likely. It's probably some asymptotes in there, but who knows. We got some information out of steps 2 and 3. I don't know if we did step 2 on this one. Well, whatever. Doesn't matter. You might have to just do step 4 in isolation and just be okay with the fact that you don't know what it looks like. Okay. So we did do the first derivative. We got this guy. So now we have to do the second derivative. Take the derivative of this. So clearly a product rule. Derivative of the first times the second plus the first times the derivative of the second. Now those both look like e to the x, but the first one I took the derivative and the second one I didn't. The derivative just happens to be the same. You'd be surprised how quickly people think, oh, he just copied the same one down. He's not doing the product rule, he's doing something else. No, it's always one of those properties. I can factor out an e to the x, and I have a 1 plus 1 plus x, 2 plus x. That wasn't so bad, not at all. Out of this, I get the second derivative equaling 0, check. Second derivative, undefined, check. Second derivative equaling 0, when one of these two guys equals 0. Well, from the bracket, I definitely get negative 2. And e to the x is 0 when? Same questions coming up, and that's how we learn. Important questions, underestimated how important they are. E to the x is 0 when? It is 0 never. How do I know? I picture the graph, it's always above the x-axis. So it's not guessing, it's not memorizing, I literally read it off the graph. That was really what we were talking about, but they're both defined, everything's good. It's not going to be undefined ever either. So I get one contender, that's not bad, it's better than nothing, I guess. Mark it off here, negative 2. Then I'm going to list everything. I have an e to the x, I have a 2 plus x, and they combine to give me my second derivative. E to the x, we just said, is always positive. 2 plus x is 0 when x is negative 2. It's multiplication to make the second derivative 0. It's going to go, double check, negative to positive. I don't guess, I don't memorize, I just do it very quickly. You have to be sure. So I have a positive and a negative, negative. Positive and positive, positive. Bending down, bending up. Again, not a full bend necessarily. I don't know what's going to happen. I'm just reminding myself what the plus and the minus means. Okay. Let's write our sentences. Actually, let's do it over here. F is concave up on certainly negative 2 to infinity. Infinity always gets a round bracket. Negative 2. What kind of bracket does it get? So in the process of writing these sentences, I am sort of answering the inflection point question, sort of. I'm finishing the inflection point question at the same time. Inflection, there's sort of a hand-in-hand situation here. Points at it. Oh, no one answered me yet. Does negative 2 get a round bracket or a square bracket? That was my question. Square bracket, because I'm referencing the original function Actually, in this case, yeah, they're all happy with all x values. But the original function is the one I'm making a statement about, and it is defined everywhere. The y value will be negative 2 over e squared, whatever that is. I don't know. Don't really care. It exists. That's the most important thing. When I go to graphing, sure, I need to put the y values in their relative places, but right now I just care about existence. So that also means that, yeah, inflection point. Because it came out of my check, there is a point, concavity changes, all three conditions are met. And let's finish the sentences here. Concave down, of course, on negative infinity to negative 2. If I include it once, I'll include it everywhere. All right, so now it's a little unfulfilling here. I'd like to see the graph and how could this possibly happen. Sure, we could do that because we have some information from prior examples. Ichi-I, okay. So I'll zoom in a little bit here. We had a critical point at negative 1, if you look back, remember, and we saw that it was going to make a little cup there. If you did step 2, and I don't think we did step 2 on this one, in combination with step 3, we would have a horizontal asymptote over there, and just going off to infinity on the other side. We would have a y-intercept of 0, and that's pretty much what we have, right? Increasing on the right side of negative 1, actually decreasing on the left, increasing on the right. Okay, so somehow we have to come down to that turning point and up. Okay, it's fine. The concavity now tells me exactly how this shape looks. Let's do the right side first. I need to clean this up a little bit, right? So I don't have the symmetry, right? Don't try and balance this perfectly. It's going to be a little tight on the right side, a little steep rather. That's okay. And on the left, see bending up? No, it's bending up through to negative 2. Let's put that over here. And if you actually calculate the y values, the inflection point sits a little lower. Not necessarily half. I can't remember if it's halfway. I don't think it's perfectly halfway, but it's in between this turning point and the x-axis. Of course, it has to be. There's no other way, right? So let me just clean this up a little bit. So now I'm going to turn at my critical point. Oops, no, that's too fast turning. This side of when I can't see my hand is deceptively hard. I'm going to turn up, or bend up rather, all the way through. And then I'm going to change in the way I bend to bend down towards the horizontal asymptote. And if you look at the derivatives, none of it was really complicated. I didn't have a lot of potential critical or inflection points. My table wasn't big. The derivatives were easy to simplify. Everything was pretty straightforward in terms of complexity. Yet I get more interesting graphs. I get graphs that have an asymptote on one side, and a turning point, and changing in the bend. It's interesting stuff. So I like this middle ground. This exponential component type function is the sweet spot. Now I can't just ask you this type. I have to mix it up, unfortunately. Otherwise it'll get boring. But this is sort of the sweet spot. Not too easy. I don't know what the graph looks like. I'm going to have to do the analysis to know. Even if one of the pieces up here, even if one of the pieces changed, if I change that to an x squared or I change it to an e to the negative x, the graph changes drastically. So there's some interesting stuff within this type of function as well. Right, are there any questions at this stage? So we have done all our main steps. We did the warm-up step. We did the asymptotic behavior step. Let me just go and see here what our schedule looks like while I'm thinking. We did increasing, decreasing behavior. We now did concavity. Those all paint the picture perfectly, providing us all the information start to finish. But we are a little bit ahead of the game, right? All of this was done in advance for midterm 3, right? Midterm 2 only stops at logarithmic and exponential functions, really focusing on derivatives of all these kinds of functions. So it's on the course website what topics are covered by the midterm, but this midterm number 2 will be from everything about the derivative. Topic 4, limit definition of the derivative, all the way to topic 7, log and exponential functions. It's really all about the derivative. So we'll put a pin in this whole graphing thing and then revisit it pretty much all of next week, where we want to do everything from start to finish, and we want to actually focus on the graphing, piecing all the information together. But I know everyone's focused on the midterm right now, which is perfectly understandable. Are there any questions about anything? I think I answered your question already. Topic 4 to topic 7, based on our numbering. Any other questions on the midterm? Oh, we have some Q&A time Sunday morning, if you like that kind of thing. Or as you study and you realize, oh, what's happening? I need to ask a question. There is time. Of course, you can do it by email. I may have said it. I can't remember if I did. I'm pretty sure I did somewhere. The homework number 2 answers are on the website, but unfortunately, it's only in video form. I lost the PDF, unfortunately, but it is there. The video is there. So you just have to scroll around if you want the answers to different things, but everything is there. I just didn't have the patience to rewrite everything when we have a video detailing all the answers to all of it. It's not unrelated, it's a question. Oral tests have already begun. You can do it anytime during any Q&A session. You say, hey, I would like to do my oral test. I say, okay, let's do it. We do a private call so no one can listen in, and I need to see your face to make sure you're not paging in a book or anything, right? I ask you a few questions, you answer them, 5 to 10 minutes later, you're done. Uh, you know, yeah, don't prioritize that above a midterm. Midterms are definitely more important. But if you think about it, it's best to get it done earlier just for peace of mind. And if you think about it, I can only ask you, let's suppose you're doing the oral test right now or Sunday or whenever, right? I'm only asking you up to maybe asymptotic behavior, right? Not anything too recent. You, of course, have to review. But if you did it a month from now, let's suppose you did it on April the 9th, just randomly. Now I can ask you things about almost everything. Everything we've done roughly up to that point. So I don't really understand why people leave it until the end, because then your test covers more topics and it's more difficult. The sooner you do it, the easier it's going to get, to a degree. But it is ultimately up to you. I don't care, as long as you get it done at some point. We have lots of Q&A sessions. Look at all these red ones. Okay, that's a holiday, but still, most of the red ones. So don't leave it until the end, though some people always do. Totally up to you. Totally up to you. I don't mind. Any other questions? Well, maybe as you start to study, you think of some questions. Remember, no graphing questions on this midterm. None. That's for next midterm. We just wanted to get ahead of the game. It happens, unfortunately. All right, I will stop rambling on and let you enjoy your weekend until I guess we'll talk again Tuesday, but I'll sort of be here on Monday for the midterm. Until then.